Hello, ladies and gentlemen. Welcome back to the Ephemeris podcast. I'm your host, Aphelion, and this is what will be the first episode of season 4, where we're bringing in some guests to the podcast and getting some new perspectives on some really interesting ideas in the world of astronomy. Today, I have a special guest, Isla. And go ahead, Isla, and introduce yourself if you wish.
Yeah, so I'm a physics major. I'm a freshman, and I'm really passionate about exploring, things in astronomy, but I'm also really into like fundamental physics. So I've been like working with that. I've done some computational astrophysics in the past as research, and I'm now working on some particle physics.
All right, thank you very much for that. Today's topic that we will be talking about is going to be neutrinos, and so I'll just provide a quick introduction for those of our viewers who are not familiar with the subject, um, and then we will get into a discussion with Isla about some more interesting stuff. So, um, we have briefly talked about quantum particles on this podcast before, but I've given very watered down descriptions and sort of just a little bit of fermions and bosons, but nothing further than that. So, um, why don't we discuss in detail what the map of all the forces and particles looks like in quantum physics? Firstly, the division of quantum particles into fermions and bosons. Bosons is important. So fermions, once again, are the quantum particles that make up matter. And within fermions themselves, there are the up, down, top, bottom, strange, and charm quarks. So the first sort of section within fermions is quarks, and the two quarks that are relatively easy to understand are the up and down quarks because they're a little bit more relatable to us. A neutron is made of two down quarks and one up quark, and the proton is made of two up quarks and a down quark. The rest of the quarks, they typically form pions, but I think I'm going to leave that as a conversation for a different podcast episode. Just important to recognize that they are there, and anything relating to how they form pions is probably a separate subject. So the second section within fermions is leptons, and some of the leptons include the electron, muon, and tau particles. And electrons are very familiar to us, but a way to imagine muons and tau particles is to imagine them to be electrons, but more mass and being involved in higher energy collisions out in probably space. So fermions consist of the quarks and the leptons, and then the bosons, which is the other division we made at the beginning. They are the force carriers of the quantum particles, and they team up with quarks to generate two of the three main fields that we know of today. So gluons team up with quarks to generate the strong force, which is what holds the nucleus of an atom together, and the W bosons, Z bosons, and photons interact with quarks and some leptons to generate the electromagnetic field. And so the Higgs boson particle, which is also among those boson particles, it's the last of the five, and it's a scalar boson. And that is that Higgs boson particle is truly a spectacle in and of itself. So we're also going to leave a different podcast episode for talking about the Higgs boson. But, but, but there's something very important that we left out in our description of leptons. And to talk about that, we have Isla, and we're going to be talking about the neutrinos, which is within the lepton section of the fermions in the quantum particle, I guess, table, you could call it. So, Isla, can you give us as best of a description as possible as to what neutrinos are?
Yeah, I can. And I think a good way to start approaching this question is to actually think about where neutrinos came from in terms of our physics, research. So in around the 1930s, a physicist by the name Wolfgang Pauli noticed that there was an energy discrepancy in this process called radioactive beta decay. And beta decay is where you have an unstable nucleus that basically decays into some constituent particles. In this case, it converts a proton into a neutron or a neutron into the proton with the release of an electron or a positron. Now, this process was incredibly important because they realized that there was some energy discrepancy. And like I was saying, Wolfgang Pauli realized that this energy discrepancy might be the result of a unseen particle. Um, Now, everyone in this field was a little bit skeptical about this idea of this unseen particle coming out of this interaction, specifically because if it was to exist, it would be practically indetectable. So it's a little bit difficult to, actually do much with it. However, another prominent Italian physicist by the name Enrico Fermi did in fact believe in this idea of this particle. He went as far as to give it the name neutrino, which in Italian means tiny neutral one, which is just
Mm.
adorable. And beyond, just giving it an adorable name, he went on to, do more research into this beta decay process using, this postulation that Wolfgang Pauli came up with. Now, later on, they, actually were able to detect this tiny little neutral particle called the neutrino in a experiment called, well, I don't know if it was called, but from a nuclear reactor in the Savannah power plant in 1956. Now, this was really important because this was actually, experimental evidence that this type of particle did in fact exist. And so there's been so much research going on with it as we discover interesting properties about the neutrino and so on and so forth.
Hmm. Yeah, so just a question to bring up about that, in terms of like detecting the neutrinos. What do you think, or what is exactly the thing that we are detecting when we see neutrinos in action in these very complicated sort of nuclear processes?
Right. So I think to answer that, it's a good idea to like jump into this idea of the detectors that we do actually use to measure neutrinos. And for that, I need to introduce something called Cherenkov radiation. So Cherenkov radiation is this process where you have charged particles that are traveling at incredibly fast speeds in some medium. And because they're traveling at these incredibly fast speeds, in fact, I should mention when I say incredibly fast speeds, I'm talking about near light speeds in a vacuum. There is this effect, almost like a sonic boom, which causes them to release light. This is actually because the speed of light in a vacuum isn't the same as the speed of light in a medium. For example, the speed of light in water is around 75% that in a vacuum. So that's where this sonic boom effect comes from that, creates this light release that we pick up. And this light is called Cherenkov radiation. And we can actually use this to detect neutrinos. So there was this one experiment in Japan. I forgot the name of it. If I knew it, I probably wouldn't be able to pronounce it either, but it's a really fascinating experiment where basically they had this pure heavy water. And because it's pure heavy water, it's actually dense enough to interact with neutrinos, those water molecules. And so what ended up happening is you would have a neutrino hit the water molecule and an electron would recoil off of that water molecule. And the electron would be traveling at incredibly fast speeds. And this would release Cherenkov radiation. Now, our detectors, which are called Cherenkov detectors because they use this radiation process, are actually able to pick up this recoiling from the electron. And from looking at the outgoing velocity of the electron, as well as information about the angle at which it comes from, they're able to actually figure out information about the incoming neutrino.
Hmm. Okay, that I think is a really, really good explanation about the detectability of neutrinos and what exactly they are. And it seems like it entails a lot of energy effects depending on, the mediums that you're using. Sort of the energy of neutrinos, does it tell us anything else about the neutrino, like perhaps mass or any other related characteristics of other, like that exist in other quantum particles?
Right, so you brought up this process of mass, and mass for neutrinos is incredibly interesting of a subject. Neutrinos are interesting because they have this process called neutrino oscillations, where I don't know if you mentioned previously in your podcast, but
Mhm.
there's flavors of particles. I don't know if you mentioned that before, but it's almost like a different, yeah, okay. So particles in the standard model, and the standard model is perhaps our best model for understanding these fundamental interactions. They predict that these kinds of particles come in something called flavors, which are kind of like the species of the particle. And
Mhm.
so for neutrinos, you have three flavors. You have the electron neutrino, the tau neutrino, and the muon neutrino. And so with these three neutrinos, they were actually able to realize in this really interesting experiment that I could go on and on about called the homestake experiment that neutrinos undergo something called neutrino oscillations, where they oscillate between these three flavors.
Mhm.
And so this process is incredibly interesting because it tells us actually that they have mass because this superposition comes from something called a mass eigenstate. It's a bit complex, but basically it's telling us that because neutrinos undergo these oscillations, they have mass. And a
Mhm.
really interesting thing about neutrinos having mass is the fact that the standard model itself actually predicts that neutrinos shouldn't have mass.
Mhm.
And I can actually tell you why it predicts that they shouldn't have mass. So, in particle physics, all the particles have something called chirality, and it kind of just talks about their left-handed and right-handed counterparts. So just know
Mhm.
that, it's a whole subject you could go into later on.
Mhm.
But neutrinos basically are only ever found or seen in nature as being left-handed. Now, this is odd because for something to have mass by the standard model, it has to have both a left-handed and a right-handed counterpart. And the Higgs boson, which I know you said you could talk about later, but it gives
Mhm.
basically mass, is supposed to be able to couple these two left-handed and right-handed fermions together.
Mhm.
However, because the neutrino itself is only left-handed, it doesn't make sense for it to have mass, but it does, and it comes about in this process with neutrino oscillation. So that's a really active field of research right now and something that they're trying to understand because, in fact, this is kind of showing that the standard model is probably incomplete, which is amazing because there means there's new physics for us to explore. And you were asking specifically about the energy of the neutrino in these detectors. I kind
Mhm.
of went on a tangent here about mass. So we can't really figure out their mass using their energy, but we can kind of like with theoretical calculations as well, do like an upper limit approximation, but can't really figure out their mass. However, by looking at the track that these neutrinos leave behind as they enter the detector, we're actually able to distinguish between the flavors of these neutrinos. So if it's an electron neutrino that's passing through this medium, you can expect to see kind of like a sphere, almost a bulb effect, and that's because of electron showers, which create something called a cascade effect, and that's the bulb. Now, for muons, what you'll actually end up seeing is like almost like a streak, and those will be your electron or muon neutrinos.
Mhm.
And then for the tau neutrinos, because they decay quite quickly, you're going to also end up seeing kind of like a streak and then another kind of bulb shape. So it's almost like a mix between the electron neutrino and the muon neutrino. But looking at these tracks and analyzing the data, we're actually able to distinguish between these three flavors of neutrinos, which is incredibly useful because it gives us insight into not only where these neutrinos came from, like what kind of interactions, but
Mhm.
also, allows us to do research into neutrino oscillations and to
Mhm.
understand the properties of neutrinos.
All right. Yeah, thank you so much for that. Because honestly, like uh, it went even beyond the question that I asked, and something I was going to follow up with was how do
Right.
we distinguish between the types of neutrinos and like why
Oh,
does it matter? And you like completely cover that question as well. So
right.
the next thing I want to ask is where do we find neutrinos? Like what are the places that we're looking for them in terms of like the grand scheme of things? And yeah. What is your opinion on like how we can improve our ability to just like find them in all sorts of places in the universe?
So your first question was really entertaining to me because where neutrinos come from, they come from everywhere, but there's actually a source you're probably the most familiar with. And it's a source that we are all very thankful for because it is the sun. Now, the sun is probably no, not probably, it is like the biggest nuclear reactor that we have here in our solar
Mhm.
system.
Yeah.
And in the core of the sun primarily gets its energy from something called proton-proton chain interactions. And I could like show you the equation for it, but I'll just like tell
Mhm.
it to you. So
Yeah.
basically what ends up happening is you have four hydrogen nuclei, which hydrogen nuclei are pretty much just protons.
Hmm.
And so they fuse together to create an isotope of helium, helium-4, with the
Right.
release of two positrons, two electron neutrinos, and electromagnetic radiation. Now, this electromagnetic radiation, also known as light, is something that we are, very familiar with and
Mm.
thankful for. And
Yep.
it comes from the energy discrepancy in E equals mc squared. So there's some mass
Hmm.
that goes bye-bye. And so you get energy that comes from that in this form of light. And so, yeah, so electron neutrinos, come from these kinds of solar interactions, and we know them very well as solar neutrinos. And there have been a lot of experiments going on to actually measure solar neutrinos. As I was saying before with the homestick experiment, um, that's actually one of the ways we realize that neutrinos undergo oscillations because they were looking at neutrinos, especially specifically electron neutrinos that come from the sun. They were looking at this process where an electron neutrino interacts with chlorine, and that produces an electron and argon. And this
Mhm.
process is only possible through, this nuclear interaction. It's not possible via chemical reactions. And so they were actually able to determine that they were seeing only around a third of the electron neutrinos that they were supposed to coming from the sun. And, this led to a lot of speculation as to what's happening. And that's how they were able to eventually realize that neutrinos undergo oscillations. And since there's three different flavors of neutrinos, you can expect to see if they're oscillating between the three, that you'd see around a third of the electron neutrinos you're supposed to. So this source
Mhm.
of electron neutrinos from the sun has been incredibly useful for our research. But electron neutrinos, or not just electron neutrinos, but neutrinos in general, come from so many other sources. Black holes, like quasars, they emit
Mhm.
neutrinos, and it's something that we're actively looking into right now. There's also a lot of ideas with supernovae and neutrinos. And maybe when a supernova is, undergoing its supernova process, that
Mhm.
neutrinos actually play a crucial part into the nuclear interactions that happen within the supernova. But again, this field of research is like really new and people are like looking into it. So there's not a lot I can tell you about supernovae and neutrinos that at least I'm familiar with because no one actually really knows the answer to these kinds of questions. But they come from everywhere, specifically a lot of nuclear interactions. So,
Okay. Yeah. Um, so another thing that I wanted to bring up is beyond sort of seeing neutrinos coming from the sun and coming from sort of stellar phenomenon like black holes and supernovae, um, neutrinos are an integral part of sort of the Big Bang as like the time as we crunch the time towards zero of when the universe began. So, can you sort of speak to that idea and how neutrinos relate to the Big Bang?
right. So, as you were saying, as we, approach zero, you can see there's something called the cosmic neutrino background. And basically, neutrinos are one of the oldest particles that we know of. They appeared in the universe I think 2 seconds after the Big Bang. And so they're everywhere in our universe and they're incredibly low energy right now. And so they build up something called the cosmic neutrino background. Now, this is specifically interesting because it's another way we can begin to look through our universe to begin to see, I guess, early times in the universe and look at that kind of history. Specifically, something that's very interesting about neutrinos is the fact that they might be a Majorana. Hope I'm pronouncing that right, Majorana fermion, which basically just means that a neutrino could be its own antiparticle.
Mhm.
Now, this is really interesting because this process means that something called double beta decay, where basically you can have two neutrons and they'll begin to decay and you actually end up with two protons and I also believe two electrons. And what ends up happening is that a neutrino is released in this exchange and they annihilate each other. And so this almost acts like a matter creation process. You start from two neutrinos and you end up with or so you start with two neutrons and you end up with two protons and some electrons. And so that looks like a matter creation process. And we know in our early universe that there was more matter than antimatter. And we're still trying to figure out why that is. And so neutrinos actually might be a source for this. If we're actually able to prove that that the neutrino is a Majorana fermion, then we're able to kind of have an idea, perhaps, as to why this matter asymmetry exists in our universe and
Mhm.
basically why we exist at all.
Okay, yeah, thank you for that. Because I mean, it's easy enough to sort of say that like neutrinos relate to the Big Bang and they're super important, but kind of seeing them almost as like these particles that explain a lot of discrepancies and sort of really bridge together some of the ideas that we see when we crunch the time towards zero. I think it's sort of important to get that insight. And so, I mean, sort of wrapping up a lot of the ideas that we've talked about here. Um, Neutrino astronomy, as we know it, is an emerging field of astronomy and astrophysics. Can you tell us more about the field and where it's going?
I would absolutely love to. Neutrinos are one of my favorite particles, and it's because there's so many different ways that we can look into them and, kind of see their effects in our universe. So specifically, because I know you're really interested in astronomy here, there's this
Mhm.
really interesting project called IceCube, and it's basically a detector in Antarctica, which IceCube, Antarctica, I love that. Um, and basically, as neutrinos stream through the ice in Antarctica, because the ice is really dense, this process of Cherenkov radiation that we, talked about before actually happens, and we're able to detect it. In fact, IceCube has over 5,000 light sensors to pick up this radiation, and they're able to look at the tracks that these neutrinos leave behind, and from there, they're able to, begin to do neutrino analysis and so on and so forth. Now, this is the largest detector in the world, so it's really cool, and it's something that we're actively working on. And the reason why I brought astronomy into this is because they saw a steady stream of neutrinos emerging from this one constellation, from IceCube. And so then they had a bunch of other telescopes turn their attention to this constellation to see what's going on, and they actually found a supermassive black hole. So this just shows you the potential for neutrinos, um, in all different kinds of fields of physics. In fact, IceCube is not just looking at, things like black holes, but things like supernovae. It's looking into, unique properties of neutrinos like neutrino oscillations, and it even has the potential to even look into things like dark matter. Specifically, another really cool thing about dark matter and neutrinos is coming from Fermilab. So I don't know if you know a lot about Fermilab, but um, they're constantly doing incredibly wild work that passes over my head, and it's just so exciting to look into. But one of the things that they're currently looking into is something called sterile neutrinos. So we talked about neutrinos as having three flavors before. However, some people say that there actually might be a fourth flavor of neutrino. And so why do we need this fourth flavor of neutrino? We're just like adding flavors now. It's like, Starbucks or something. Like,
Yeah.
no. So the reason why actually is because in the Los Alamos lab, they had a liquid scintillator neutrino detector, which basically noticed that they were picking up way more electron neutrinos than they were of the other flavors of neutrinos. There was this inconsistency in these neutrino oscillations. And this anomaly, they thought, could perhaps be resolved by looking into a fourth flavor of neutrino. And so, of course, you can't just like have one detector, like, oh, we discovered this. No, you have to repeat your experiment to ensure your results are, correct. And so they repeated this experiment multiple times, and the results basically said something different depending on who you asked. Now, some
Mm.
physicists, looked at these results and said, this looks like misunderstood background, like that's what this is. Now, some other physicists said, oh, we were seeing this anomaly being repeated each time we do this. Maybe it's the result of a fourth flavor of neutrino. And because I like
Mm.
that idea better, I'm going to talk about that.
Sure,
Um,
go ahead.
yeah. So the sterile neutrino specifically has the name sterile, and it's not just called sterile for no reason. The reason why is because it doesn't interact with the weak force, the strong force, or the electromagnetic force at all.
Mm.
It only interacts with gravity, and because gravity on a quantum scale is pretty much negligible, it basically doesn't interact at all. So
Mhm.
detecting it is incredibly difficult because even with the other flavors of neutrinos, which I'll call active neutrinos here, they interact with the weak force, and that's why they come about in decay processes, because decay processes are mediated by the weak force.
Mhm.
Um, so, we have at least some ways to detect neutrinos, even though neutrinos themselves are very, very difficult to detect. In fact,
Yeah.
they don't interact a lot at all. In like the last second, around 100 trillion neutrinos just passed through your body, and you didn't
Hmm.
notice any of them.
Right.
So, right. So, sterile neutrinos are even harder to detect. So, Fermilab is looking into, this method of detection. And in fact, they said that sterile neutrinos themselves, if they did exist, they could explain dark matter. Perhaps sterile neutrinos are the dark matter that we've been looking for. So these are
Mm.
just some
Yeah.
of the projects that are going on. We're funneling a lot of money into neutrino research. So it's a really active field, and I'm so excited to
Mhm.
see where it goes.
I like how you got into sort of the detectability of neutrinos and how like it's really an active effort with,
Yeah.
all of the things that are going on and all of the moving parts. So yeah, that's really all I had in terms of questions for, what neutrinos are and sort of the whole purpose that they serve with a lot of the theory that we have currently. Is there anything else that the viewers should know?
I mean, they should know that neutrinos are just incredibly like powerful of a tool for exploring our universe. I would definitely look into, initiatives like IceCube and Fermilab and just, oh, look into the Hosek experiment. Just read about it. It's so fun.
Mhm.
So yeah, I would just really encourage you to do your own research because neutrinos are just so fascinating. And the fact that we can barely detect them just makes them so much more interesting to look at.
Yeah, and with a lot of the sort of quantum physics, it's really
Right.
important to, sort of get into those deep dives of like what exactly is going on with, the specific particles and like how does it relate to everything else and sort of the principles. So yeah, thank you so much for all of the discussion that you brought to the
Of
idea of
course.
neutrinos on this episode. And that pretty much concludes what I have for you all today. Hopefully, you enjoyed the first episode of a completely new format. Thank you once again, Isla. And until next week, I will see you all later. Peace.